So I've been working in the Himalayas since 1980. 81. I first went to Ladakh in 1981.
1981.
And I've been back almost every year since to some part of Nepal, India, Pakistan, Bhutan. So I love it. And yes, the Himalayas is my second home.
So now when are you planning next?
I'm going to Nepal in mid-September for 2 months.
So what is your purpose of going there?
I'm leading a trek up to Mustang for Oxford, Cambridge alumni. And then I'm staying on for 1 month to the HKT meeting is in Pokhara in early November.
Okay.
So I have a charity in Nepal that's set up after the earthquake, rebuilding one of the villages where all our porters came from.
Okay.
And we're now setting up a trekking company there to get them some employment and income.
Oh, that's really good.
I'm going out to see how that's getting on. But no, it's very good. The village, we've now built a new school for 180 kids and a new little hospital. It's a very, very remote village. It's right up on the tree line. Beautiful place. So I like to put something back into the local economy that I've had so much pleasure from working in the Himalayas that everywhere, especially Zanskar, Ladakh, Nepal. So yeah, I love it. So Ritesh, can you see my screen?
Yeah. What have you displayed now?
Yes, it's displayed now. So I'm just going through the first few slides and it seems to be fine. Can you see that?
No, I am not able to see.
That's weird.
I can just see your launch. I can see.
So I've put him on as a co-author because a lot of this data is his micro fossil work. So okay. I'm not a paleontologist, so I'm going to talk about the tectonics, and but he will be logging on to the talk. So if there are any questions about fossils at the end, it should be directed at Owen Green.
Okay.
My talk is mostly about the tectonic story of the India-Asia collision.
So that is the main theme. You know what we are looking for now, and probably I think you'll be striking the nail. You know,
great.
And we look forward to see how things have been moving. You know.
Okay.
Because,
excellent.
Mike, what happened was. I also started my career as I didn't know, in my graduation day, I just heard about Medlicott, and he found some fossils from Kasoli. That was low Miocene times, Kasoli formation.
Yeah.
And I belong to Kasoli, so that is how I got interested in geology. Not geology actually, but my main interest was Medlicott got some fossils from Kasoli. So I should get some fossils. How he got it, you know, in 1864, and then nothing happened. And then I started my search, and by the time I completed my graduation, I had the largest collection of fossils from Kasoli.
Excellent.
But that was it, and then I continued my research in that, and then I almost did my PhD in that.
Right. Yeah.
At that time, it was like collecting fossils, identifying them. I was not a taxonomist, so I took help with Birbal Sahni Institute of Paleobotany, and then gradually we were able to identify about 6 species, you know. And okay, then we just reported it, but then it turned out that these species are nowhere found in Himalayas, and they are confined to the Malaysia, Indonesia, and Andaman. So it was like Alfred Wegener, rewriting Alfred Wegener's theory, you know. He got Glossopteris, Gangopteris, and this continental drift theory, and then my Kasoli formation. And then similar things were happening in Ladakh also. We found some fossils, and then they were like almost similar to the ones we found in Kasoli and Sabatu. And then this interest gradually built up, Then I was, for the last 20 years, I was in Ladakh. I was working for the Tibetans who migrated after this Chinese aggression. That was my first project. I was asked by WaterAid, a UK-based NGO, to do some exploration for groundwater for the Tibetans who migrated from. So that is how from a paleontologist, I became a hydrogeologist.
Right.
So that was, that was my first project, and then that the 3,800 Tibetans who were living from Hanle, Sumdo, then Choglamsar, and the entire Nimmo. So all along this axis, I had to explore, and in 1997 we started this. 1997 we started, and 1998 these 3,800 Tibetans had 24/7 water, 24/7, 24 hours. So that was my. But when I was doing so, my interest in fossils always was there, So then we did lot of discoveries, and then gradually. Now I was free, so I had got good collection of fossils, and then the idea of making this fossil museum came up. So initially I donated a lot of fossils to the various museums I used to go, but then the story didn't come up, the way I wanted. So now we are making this fossil museum in Kasoli. So I think I'm not boring you.
No, I'm interested in how the Tethys Fossil Museum started.
Yeah. So then the government gave me some land, then the other government came, and then it didn't work out, They stopped it, and then there was a lot of politics. So then I got a piece of land where I used to put my drilling rigs. So that I vacated that land and then made this my dream project, gradually I used to divert some funds, make a build, bought this land, then make a building, and then now almost it is 5th October is the deadline which we have set for ourselves to just launch it on the World Heritage Day. It's I think October 7th or so on World Heritage Day we plan to organize the World Chandigarh to Kasoli from Shivaliks, crossing the Shivaliks, and then going to across the main boundary fault, main frontal fault, crossing main boundary fault, and then entering into the Kasoli formation after seeing the Tethys, the Sabatu sequence, the marine, and showing all we have identified about 4 or 5 geoheritage sites also on the way, where we'll be showing main boundary fault, then oyster beds, molluscan beds, where we collected whales, sharks, and then the plants, trees, and then we go to the museum, where we have almost all the fossils from stromatolites we discovered from Cornwall. So these are 90% of the fossils are from Himachal and Ladakh only. So we have these fossils spanning from 2.5 billion years to almost stone tools discovered by man. So the entire fossil museum is divided into 2 parts. One is the natural evolution, dedicated to Charles Darwin, Mendel, and Medlicott, and that is showing the natural evolution. And the second one is the man and his environment, what man has done to the environment after the stone tools, and then after the glaciation, how things moved in the civilizations. So then we have this Rakhi Gadi and the Harappan civilization fossils, and then industrialization, how things moved after that. So we have almost all the fossils of all the eras. We have Ediacara, we have trilobites, we have almost the very good ammonoids, the Glossopteris, Gangopteris, and then fossils of dinosaur eggs, and then whales, sharks, almost oysters, very good oysters, very large oysters also. We have an oyster wall which we have made now because there was a lot of fossils which we collected while the road was being cut, and then So this is turning out to be a very, but it is now this exercise. So our main interest was when the first sea, Tethys Sea, so-called Tethys Sea or ocean, when it gradually shallowed up, and then how things moved. And then my interest about knowing, because this entire exercise led us to many new way of thinking about Himalayas, because we got the same fossils from Kasoli and same fossils from Ladakh, almost homotaxial equivalent, and then all these equivalent to, they are nowhere found in Himalayas, then taking the entire Himalayas again back to equator, and then depositing them and retransporting them. So things became very interesting for us. But then I just wanted to have a global view of all the people who have been working on this. So we started with Peter Molnar, then Nigel Hughes, Robert Spicer, then we requested them, and everyone was very kind enough to accept our invitation. I think now we are almost approaching the time, huh?
Sure.
So I think maybe we can discuss later on.
Sure. So where is the Tethys Fossil Museum? It's in Delhi.
Ritesh, no. It's in Himalayas. It is in Kasoli.
In Kasoli. Okay, right. Okay.
It is very much in Kasoli, and the Tethys Museum, which I bought, the land is situated on the confluence of you can say the time when the Sabatu Sea was squeezing up, and the continental conditions were arriving. We have the contact. So that is the land which we bought was on the contact between the Sabatu and the white quadrite band. After that, we have the Tachai formation. I don't know whether you're familiar with this terminology or not, but that is the Tethys Sea, which is squeezing up, continental conditions arriving, and that is where we have our museum. And the entire museum is made of Kasoli sandstone, about 20 million years. We don't use any wood for this museum. And the entire museum is made of stones and stones and stones only. So that is this part. We don't have any wood till now. And I hope we will be able to maintain this till the time we complete,
Okay.
So we have, you have been to Kasoli?
No, I don't think so.
So I think now when you fly to Nepal, or you want to go by road?
No, we fly to Kathmandu and then bus. But I do go to Ladakh. I was in Ladakh in 2018.
Oh, okay. So
So I'm working with Talat Ahmed.
So Talat, I have requested Talat to be here, and he will be chairing this session.
Oh, right. Okay, good.
So I think we will have him, and then he will be welcoming you on behalf of this fossil museum. Yeah.
I think he's now in Dehradun.
No, he was in Ladakh.
Yeah.
For a conference, and then I think he's in Wadia now, I think.
Right. Okay, good.
So I just requested, and he was kind enough to agree to share this webinar.
Right. Okay, excellent. Good. So it starts at 2:30, is that right?
Yeah. We will just start it.
Okay.
So I'll just see. So we have the participants now. But I like you to visit Kasoli one day, and visit this maybe on if you're planning your trip in September,
Yeah.
So maybe you can come in October.
It'll be
if
difficult.
It is possible.
Yeah. Maybe next year, Ritesh, I will come to Ladakh. then it can be more firm.
Okay, okay. I think how much, what's the time now?
I have 7 minutes to go.
So yeah, we can just wait till then, huh?
Okay.
I'll just check with the Talat sir and then see if he's,
Sure.
he has not forgotten, huh?
Okay.
So he's just joining, Saleh.
Okay.
I just had a word. He said that it's before 7 he'll join.
Okay.
So how come you became interested in this, you know?
Well, I was a mountain climber when I was very young.
Mm-hmm.
So I first went to the Himalaya in 1980 on a climbing expedition to Nepal, Langtang Luram.
Mm-hmm.
And I just absolutely loved it. Trekking in the Himalayas was the best thing ever. And I always wanted to go to Ladakh and Zanskar. So as soon as it opened in 1981, I went straight up to Leh, spent 3 months trekking from Leh to Manali, and then back through Kashmir. And as soon as I saw Zanskar Ladakh, I just loved the place. Wonderful, fantastic geology, wonderful people, very hospitable. Just everything about the place was great. So I ended up working in Ladakh for 20 years. Been back ever since. And I was there 2 years ago, just before COVID, working in the Zanskar, in the Suru Valley region, near Nun Kun, in the metamorphics. So I've been working on the sediment. I'm a structural geologist, so I work on the structures of the Tethyan Himalaya, Spontane ophiolite. We spent 3 years mapping all around the Spontane ophiolite. And then I went on a winter trip to Zanskar, walking on the frozen river, which was absolutely wonderful trip in January. 3 of us from UK and 4 porters from Pishu village in Zanskar. And we walked from Leh to Padam. And then that was the most fantastic trek I've done, but very, very cold.
So Talat sir is not able to join. He has some problem, you know.
Who? Talat?
Okay. उसी नंबर से okay. ज्वाइन मीटिंग करेंगे तो आपका आ जाएगा, अगर वो लिंक मिल गया ना आपको। हाँ जी, हाँ जी, जूम पे, जूम पे। हम्म। हम्म। एक ही करो आप, जूम मीटिंग का खोलो और वो आपके पास आ जाएगा, कोई दिक्कत नहीं आएगी फिर। हाँ, अरे अच्छा, ऐसा तो मुश्किल है वैसे, सबका तो ऐसे कभी आज तक कोई प्रॉब्लम नहीं आया था। हम्म। नहीं नहीं, यही है सर, और तो कोई प्रोसेस है नहीं हमारे पास। अनेबल टू ज्वाइन वो क्यों आ रहा है आपका? ओहो, तो सर फिर नहीं नहीं, जूम पे करना है सर, जूम पे करना है, जूम पे, जूम पे करना है, जूम पे करना है, आप देखो एक बार। हाँ, Hello? Okay. So, in 1 minute, he'll be coming, huh?
Okay. I'm ready to start.
Hello? Ritesh?
Talat.
Hello. Yes. No, hello.
Great to see you.
Yeah, thank you so much. There was some problem, but now I have sorted it out.
Excellent. So, good.
Yeah, very nice. So I don't know. I missed. Maybe I have to introduce you, or somebody has done it.
No, I think we're starting now, Talat. So I think it's.
So they will tell me. Then they will tell me how to introduce yourself.
Shall we start, Ritesh?
Yeah. I think I'll just. Where is Ritesh now? Hello.
Yeah, he's there.
Hello, Talat sir.
Yeah. Shall I introduce?
So you can just start, sir.
Okay. So it is pleasure to invite Mike Searle to this special meeting on the timing of India and Asia collision and formation of Himalaya. Professor Mike Searle is a professor at the Earth Science Department of the Oxford University, and he works on the geological evolution of Himalaya, Karakoram and Tibet, as well as the geological evolution of Southeast Asia, particularly Burma, Thailand and Vietnam. He has also worked for 40 years in Oman, UAE Mountains and Eastern Arabia, as well as Jordan, Syria, Scotland, and Cornwall. He has published over 230 papers in leading international journals, 3 books, including Geology and Tectonics of the Karakoram Mountains, 1991, with the new Geological Map of the Central Karakoram. In the back, John Wiley and Sons, Colliding Continents, a geological exploration of the Himalaya, Karakoram in Tibet and Tibet, 2013. And he has done geology of Oman Mountains, Eastern Arabia, Springer, and he has published 6 special publications of the Geological Society. He has a very high H index of 91 as till 2021. He was awarded Murchison Medal in 2008 and elected into the Pakistan Academy of Sciences in 2014, and Academia Europea in 2019. So these are some of the crucial things, and Mike has been very actively working in different parts of the Himalaya, particularly in Ladakh, and we have been collaborating together. And we also, the good thing is that we were both postdoc together at University of Leicester. So it's very nice to have Mike with us and to listen to him. So welcome, Mike. Please go ahead.
Great. Thank you very much indeed, Talat, for that introduction. And thank you, Ritesh, for inviting me to to give this talk.
Okay.
So the title of my talk is The Timing of India-Asia Collision and Formation of the Himalayas. As Talat said, I've been working in Ladakh since 1981. Absolutely wonderful field area. I love going to India. It's my second home practically in the Himalayas. But I'm not a paleontologist. I'm a structural geologist. But I work with my co-author, Owen Green in Oxford, is a micropaleontologist. And he has done a lot of the groundwork for the data that we use to constrain the timing of India-Asia collision. Okay, so here is a image I'm sure you're very familiar with. It's taken from the space shuttle, roughly over Kathmandu, looking west along the great arc of the Himalaya. And Ladakh and Zanskar is over in this region here. It's on the Indian plate. The division between the Indian plate and the Asian plate is this line here, which is the Indus-Zangpo suture zone. It's a line of ophiolites, deep sea sediments, rocks that were originally deposited in the Tethyan Ocean that once lay between India and Tibet. And then the Himalayas are almost entirely on the Indian plate. The upper part of the Himalayas, the Tethyan Himalayas, is this region here, exposed in northern Nepal and beautifully exposed in the mountains of Zanskar. The high Himalayas is the metamorphic core of the Himalayas, bounded by the South Tibet detachment, which is a north-dipping low-angle normal fault, and the main central thrust. Both of these faults dip shallowly towards the north, and they constrain all the metamorphic rocks of the Himalaya. The active margin of the Himalaya is the main boundary thrust along the southern margin here in the Siwaliks, and that is the thrust that is seismically active today. So big earthquakes like the Gorkha earthquake in Nepal are where the Indian plate is detaching and under-thrusting the Himalayas. And these earthquakes are very regular and occur all along the Himalayan arc. So how can we reconstruct the northward flight of India? We know that the Indian continent was part of Gondwana land. It was attached to the southern continents of South Africa, Madagascar, Antarctica, and it rifted, those three continental plates rifted away about 120 million years ago. India became an island, and it moved very rapidly across the Indian Ocean to collide with Asia at some time around 50 million years ago, this time here. So we can use paleomagnetism to constrain the northward drift of India, paleolatitudes here. This paper is taken from Dewey van Hinsbergen and his colleagues. And all the paleomagnetic studies say roughly the same thing, that the southern margin of Asia, the Lhasa block, has remained in the same approximate latitudinal position throughout the late Cretaceous and Cenozoic. But the Indian plate started off way down here in the southern hemisphere, and it drifted very rapidly north, closing this great ocean between the two. So there is quite a bit of dispute between paleomagicians. The paleomag data tells you that there's been something like 200 to 300 kilometers minimum of relative shortening between the Lhasa block and India. And the question is, how has this been taken up? So there are two main models for this. The one that most people agree on is that India was a single contiguous plate. In other words, you can stratigraphically connect the Indian subcontinent to the Lesser Himalayas, the Greater Himalayas, and the Tethyan, all part of one plate, with the Neo-Tethys Ocean spanning here in between. The second model, which was proposed by Van Hinsbergen, is that there is another ocean, which they call the Great Indian Basin, roughly along the main central thrust. And they want 1,000 kilometers of oceanic crust between the Tibetan Himalayas and the Lesser Himalayas. I don't believe this model is correct at all, because a lot of people, there's been 50, 60, 80 years of research along the main central thrust in India, Pakistan, and Nepal, and there is not a single ophiolite or oceanic rock to be seen. It's a thrust fault, so you can match the Lesser Himalayas to the protolith of the Greater Himalayas. So this ocean, the Greater Indian Ocean Basin, doesn't exist. And this model is almost certainly correct in some form or another. Here's another more detailed, more recent paleomagnetic study from the people in MIT, Craig Martin and Ollie Jaguts. And this is much more sensible. They again have the position of the Lhasa block and Eurasia as maintaining a northern latitude throughout. And they also have this great basin, ocean, separating Greater India. And the two come together sometime around 50 to 40 million years ago. And you can say roughly, well, that is when the two continents, India and the Lhasa block, southern Tibet, were pretty much at the same latitude and conjoined. So by that time, the Tethyan Ocean had closed. So of course, India being an island, there's oceanic sedimentation to the west in the Suleiman Qatar ranges in Pakistan, for example, going down to Makran, and also in the east along the Burmese, Indo-Burman ranges over here. But along the main Greater India Himalaya, this is approximately 3,000 kilometers length, there was a great degree of similarity all the way through. So in my view, there was one ocean, the Neo-Tethyan Ocean, but within that ocean were major island arc sequences. And the biggest one of all is this one, the Kohistan Island Arc in North Pakistan. And when you unwind Nanga Parbat, it's exactly the same arc that forms the Dras Island Arc in the Suture Zone in Ladakh. And this was an intra-oceanic arc, very, very large arc. The magnetism lasted anywhere between 60 and 70 million years. So it was a long-lived arc, something like the Japan Mariana type arc with andesitic volcanics, dacites, rhyolites, and also intrusive granites. The Ladakh, Kohistan, Ladakh, Gangdesi granites are all intruding into this old arc sequence. So there is a suture zone to the north of Kohistan, and in Ladakh, the Shyok Suture, or the Bangong Suture, sorry, the Bangong Suture is further north still. So the island arc sequence is bounded by the Indus Suture along the south and the Shyok Suture in the north. And there's a lot of debate about the timing of collision between these two suture zones. Here's just one example taken from the paper by Bulihol et al. And it shows that the northern dipping Tethyan oceanic crust subducting beneath the Dras Kohistan arc with another suture zone to the north. At the same time in the southern Karakoram in North Pakistan, there are also arc volcanic rocks and crustal thickening events. So it's a very complicated nature in the west where you have an island arc with two suture zones either side. And from Leh eastwards, the arc disappears. So it's just a head-on collision between India and the Lhasa block. And the beauty of the Himalayas is it's actually a very simple mountain belt. It's nothing like as complicated as the Alps or the Variscan of Central Europe, for example, or the Caledonides. When you reconstruct India, it's one continuous plate. This picture on the top shows a reconstruction of the Indian plate at about, say, 65, 70 million years ago, as the Spontane ophiolite is abducting onto the passive continental margin. You have the big Mesozoic sediments of the Zanskar Range in the north, the very thin Panjal volcanics, which again die out to the east, but are very thick around the Kashmir Basin, a kilometer or so thick, and the Paleozoic sediments underneath that. And that's the sequence that forms the Tethyan Himalaya, all those beautiful folds and thrusts. And then it's bounded by the Zanskar Shear Zone, which is a branch. It's the same as the South Tibetan Detachment, the low angle normal fault, and all of these rocks between the South Tibet Detachment and the main central thrust are all the metamorphic rocks you see of the Greater Himalaya. And then to the south of the main central thrust, you have the Proterozoic overlaying the Archean of the Indian Shield with very thin Mesozoic and tertiary sediments on top. And when you reconstruct the stratigraphy of all of these, there is one horizon that is common all the way across the Himalayas, and that is the Neo-Proterozoic horizon that you see on the Indian plate in the Lesser Himalayas, the Himanta group, which is the metamorphic equivalent of the Sillimanite grade gneisses in the High Himalayas, and they've also formed the Fay Formation, which is the basal part of the unmetamorphosed Tethyan shelf carbonate sequence to the north. So there's no indication of any ocean on the main central thrust. You can match footwall and hanging wall across all of these thrusts, and India was a very nice, well-behaved, passive continental margin onto which the Spontang ophiolite was abducted. So here is a simplified model as to what was going on, going right back to the origin of the Spontang ophiolite. Surprisingly, it's a very old age. Uranium lead age is a middle Jurassic age, and it might be actually one of the very few mid-ocean ridge basalt ophiolites in the world, because the island arc on top of it, the Spong arc, is much younger. That has a uranium lead age of 88. So the arc was built on old oceanic crust, old Jurassic oceanic crust. And then all of that, the Spong arc and the Spontang ophiolite, was abducted onto the passive margin of India, probably sometime around the latest Cretaceous and Paleocene. And during all of this time, subduction was to the north, underneath the Dras-Kohistan arc, which forms another unit here abducted in the suture zone. And the subduction continued right up to the timing of India-Asia collision, when the oceanic subducting plate shut off magma supplies to the Ladakh batholith. So the youngest granites we see in Ladakh are about middle Eocene age. So one of the best methods of constraining the timing of collision between India and Asia is the sedimentary record. And this is the mountain Japuri Shan in southern Tibet, which shows the complete sequence going up from marine limestones here in white, up to continental red beds and molasse sediments. This is exactly the same as the sequence we see in the mountains of Ladakh. And in both Ladakh and southern Tibet, it's extremely well dated. So the youngest marine sediments here are lower Eocene age, belonging to planktonic foraminiferal zone number 8. And this is extremely well constrained by the micropaleontological data at 50.5 million years. So we know that after 50 million years, there was no more oceanic sedimentation anywhere along the suture zone or anywhere on the North Indian passive continental margin. Other people have suggested that you can date the India-Asia collision using the eclogites, the high pressure eclogites that we see in two main areas, Kagan in North Pakistan and Somarari in Ladakh. These are the same units, although they have different protolith ages. They are very high pressure, 28, 29 kilobars, which is equivalent to 120, 130 kilometers depth of subduction. And these are continental rocks. It's the leading margin of the Indian continental crust that has gone down to Kozai eclogite. This is what the rocks look like. This is from Kagan in Pakistan. Beautiful, fresh, garnet, omphacite, kozite, eclogite. Now, these rocks definitively tell us that the leading margin of India was subducted down to great depth and then exhumed back again along the continental margin. But they do not tell us anything about the timing of India-Asia collision. We have identical eclogites in Oman, for example, where the ophiolite is abducted onto the Arabian plate. The situation is very, very similar to Ladakh and Kohistan, but in Oman, there is still oceanic crust out in the Gulf of Oman. So you can have an exhumation of eclogites in Kagan and Somarari prior to the collision. It's got nothing, it gives us no hard information about the timing of collision. And again, these eclogites in Pakistan and Somarari are very well dated. They're all around 46 million years ago, which corresponds to very short time after the last oceanic sedimentation is occurring in the nummulitic limestones along the suture zone. And we know that from the alunite and zircon ages, which give us peak high pressure ages, there was extremely rapid exhumation up to the base of the crust, where you have titanite and rutile literally 1 million years younger. Okay, so going on to the Spontang region itself, I had a student, Richard Caulfield, working there, and we mapped all of this area around the Spontang ophiolite in great detail and did the sedimentary stratigraphy. And Owen Green was also involved in the paleontological part of this fieldwork. This is the Spontang ophiolite here. And this is all the shelf carbonate sequence here, with the Indus suture zone up here in the north. And if I show you a cross section across that, the Spontang ophiolite is this mauve unit here, overlying a lot of these incredibly highly deformed shelf carbonates of the Mesozoic continental shelf. And when you put it in the concept of the entire Himalayas, this is the Spontang ophiolite here. This is the back thrust zone along the Indus suture zone. And the Zanskar shear zone is down here. And the greater Himalayan crystalline is here. And the active main boundary thrust is down here. So we're looking at the northernmost passive continental margin of India and the deformation and metamorphism that's happening to those rocks. So this is the paper we published on the history of the Spontang ophiolite, including the uranium lead ages and the map and the cross-section and the fieldwork. It's published in Journal of Geology. So here is a picture taken looking across the Zanskar River gorge, which is way down here. And the Spontang ophiolite forms the highest thrust sheet way up here in the mountains. You probably know, anyone who's trekked up through there, you know this beautiful mountain, Singi Kangri, 5,900 meters. That's all made of the youngest Tethyan marine sedimentation. The Kessi limestone, Spanboth formation, Singila formation form all these beautiful fold structures that we see in the mountains all around the Zanskar River there. So the Zanskar shelf beneath the Spontang ophiolite is incredibly highly deformed, folded and thrust. This is a section just south of Zangla in the Zanskar Valley. And the yellow lines are just picking out bedding. So there's undoubtedly been tens or hundreds of kilometers of crustal shortening across the Indian plate margin after the collision. So again, Richard Caulfield and myself published this paper with big balanced and restored cross sections across the Zanskar shelf carbonates, and that's where a lot of these photographs are taken from. So this is published in the Geological Society of America, Geological Society of London special publication. Underneath the Spontang ophiolite is a very interesting sequence of rocks. This is equivalent to the Habi complex that we see in Oman. So it's a sequence of rocks that are all deposited in the Tethyan Ocean and were accreted to the base of the Spontang ophiolite during its abduction. Okay, getting on to the suture zone, the Indus-Zangpo suture zone, which is beautifully exposed all along the Ladakh region from Kargil in the west to Leh and beyond. And one of the best sections is down here through the Zanskar River. This is the Zanskar River at the junction of the Indus River up here. And we made this map, which has been reproduced several times in other publications, and the stratigraphy. And the stratigraphy is now extremely well known here. The last marine sediments are these guys here. These are the nummulitic limestones, which I'll show you some pictures of later on. But Owen Green looked at these in great detail during the 1990s. And then another group, Yanni Najman and Henderson, came along later and looked at the same rocks and the same sequences. And we pretty much agree that the last marine sediments are almost exactly planktonic forearm zone 8, 50.5 million years. Everything prior to that was marine sedimentation, and everything after that is continental red bed sedimentation. So there's no indication of marine sediments along the suture zone or on the Indian shelf prior to that. So the molasse sediments here, this is taken just east of Leh in the Indus Valley. The Indus River is down here. And this shows all the back folds and back thrusts in the Indus molasse sequence. Beautiful exposures there. The geology of Ladakh is really, really spectacular. This is a reconstruction of the Indus molasse basin that I made several years ago. And what it's doing is showing you the stratigraphy of the post-collisional continental molasse. Everything in brown is continental sedimentation with the famous Hemis conglomerates and the Chotsky conglomerates up here. And the marine sediments are in blue. So the Sunda formation is the ending of the final marine continuous Mesozoic, Paleocene, Lower Eocene marine sedimentation within the suture zone. There's one horizon here, the Nummulitic horizon, which is actually on top of a lower unit of continental molasse. And this is the very last marine incursion that occurs. And this is the one with 50.5 million year nummelites, acyliners, that kind of thing. So the first attempt at a basin reconstruction of this was published in 1990. This is a paper with Kevin Pickering and Dave Cooper. And then we went back some time later, and with Mark St. Onge, we dated the youngest rocks in the Ladakh batholith. So the picture on the left shows this area at Chumatang. This is east of Hemis along the Indus River. And the dark rocks here are hornblende granodiorites, granites, belonging to the Ladakh batholith. Uranium lead zircon ages of these are 57.7, exactly similar to what we see in southern Tibet. The white rocks here are these amazing network of garnet and biotite bearing Luca granites. They are not anything at all like the Himalayan Luca granites. They're final fractionates of the I-type granites of the Ladakh batholith, but with a bit of sedimentary input into the prosolith. And these dikes here, we've got precise uranium lead age dates of 47.1. So that was the very final gasp of the Ladakh magmatic episode, intrusive episode. And you'll notice the picture on the right here shows that those dikes and the granite are truncated by this unconformity at the base of the Indus molasse. So that gives us a pretty good age of the ending of I-type granites along the southern margin of Asia and the beginnings of sedimentation of the continental molasse at Chumatang. That paper was published in Tectonophysics in this paper here. A few photographs now of what the place looks like. I'm sure many of you listening in India will have been up to Ladakh. It's just a spectacular, wonderful place. The whole place is a geological museum. It should be preserved in another museum like Ritesh's of the whole of Ladakh. This picture on the top left is taken from near Lamayuru, looking towards Leh. These are the smashed up Indus melange ophiolite sequences, peridotite, and ultramafic rocks here that were ophiolitic. There's deep sea sediments of the Lamayuru complex, turbidites, cherts, all the rocks that you would expect to see in the Tethyan Ocean that lay between India and Asia. Southern margin of Asia is the Ladakh granite. This is continuous eastwards to the Gangdesi batholith in Tibet. And that is unconformably overlain by these molasse rocks, the Indus molasse, all these rocks here, which are very steep, folded and back thrust. So when you go along the Zanskar River, this is from the confluence with the Indus going down towards the Zanskar at Chilling, you can see the marine to continental transition very, very nicely. It's this line here. These white rocks are the Nummulitic limestones, and these have fossils in which you can see with the naked eye. These are spectacular nummelites from this outcrop up here. And these are overlain by the continental red beds and conglomerates of the Indus molasse. And when you go onto the shelf carbonate sequence towards the ophiolite, those rocks, that unconformity is folded. Here's a recumbent overfold with the youngest marine sediments overlain by the continental sediments, and they've been recumbently folded and back thrust to the north. So a lot of you can actually put your finger on the continent, on the boundary between marine sedimentation here, the Nummulitic limestone, and the continental sedimentation here. This outcrop is very, very special. And it's in the Zanskar River on the main gorge profile to the south. The conglomerates look like this. Most of the debris is derived from the north, from the granites, but you do see the odd, there's a red chert pebble, there's a bit of peridotite from the rocks within the Siksha zone itself. So I've been working on Ladakh on and off for 30, 40 years almost, and I've been there many, many times. One year we went in winter with on a winter trip organized by Ben Stevenson, who was my student working on the main central thrust, and we went on the Zanskar Frozen River trek. So we went in January and flew into Leh in January, and we walked from the Indus confluence all the way south to Paran, and then skied out to Kashmir to the west afterwards. Spectacular trip, and certainly one of the most dangerous treks I've ever done. This is a cross section that we made on that winter trek to show, this is all in shelf carbonate sequences here, from the Zanskar back thrust in the north to the Photoksa break back thrust here, the Spontang ophiolite is underneath, and then the towards the north, the back thrust sequence to the north. So the structures and the folding is very, very complicated. And we combined all the structural work with the paleontological work that was all done by Owen Green. And Owen is the microstructural foraminiferal expert. So he did all of the dating and the precise dating of this. And when Owen was out with us, we looked at these main sections here in red, the Kanji section, the Marling, Singi Kangri section near Spontang, and also the Gongma section to the south. And there's another study by the Italian group, Nicora et al., who were working in this region, in the Marpo region and around Dibbling. And all of that data is spectacular, and it's very precise, and it agrees with the sedimentary story, stratigraphy story, and the biostratigraphic story. So we know that the India-Eurasia collision ended with the final marine sediments at this horizon right here. Okay, so I'm not going to go through all of the fossil evidence for Ladakh because it's not my thing. I don't work on paleontology, and I strongly suggest that you either look at the papers by Owen Green, or better still, get Owen to give you a talk. Tethys Fossil Museum is exactly what he is an expert on, and he's got all of these beautiful hundreds of photomicrographs of all of these foraminifera, which we use to constrain both the timing of the sedimentation during the final marine sediments and also where they were on the bathymetrically on the shelf margin. So we can use these age data. This is the one from the Singi Chu. This is the one from around the Spontang area, and this is the one from the Kanji section. So we've got a lot of data on this, all beautiful. Owen's got hundreds of thin sections of all of these fossiliferous units. This diagram here is a summary of all the sections around the Spontang ophiolite: Kanji, Hamar, Spanvoth, Dibbling, Kesi, Kongma, Singi Chu. And what it shows is the water levels that these fossils were living at and the proximal distal relationships to the Indian continental margin. So here is a very generalized diagram showing the continental margin going from Indian plate margin here south, going out towards Tethys. And you can see that all of these various foraminifera, the alveoliners, nummulites, acyliners, and the planktonic foraminifera are the most distal ones forming in the deeper water. But they are spectacularly well exposed. And as I say, I recommend reading this paper, Green et al. It's in Journal of Geology. This is the most precise biostratigraphic dating of the transition from marine to continental along the suture zone and on the Indian plate margin. And as I say, it corresponds to P8, which is 50.5 million years. Everything after that was continental. Everything prior to that was dominantly marine. So here is our diagram showing the tectonics of how you go from ophiolite emplacement to continental collision, withdrawal of the Tethyan Ocean, and the final India-Eurasia collision. So just to make sure that the India-Eurasia collision can be defined a number of ways, and I think the sedimentary biostratigraphic way is the most accurate, but all that tells you is that is the age of the last marine sediment. The two continental crust plates could have met a long time prior to that, well, 10, 15 million years prior to that, because you don't know what substrate of the Lamajuru was. Was it continental crust, or when did that transition out to oceanic crust? So really the 50.5 is the youngest age of marine sedimentation in the suture zone. It must be older than that, the closure of India and Asia. And this corresponds very nicely to ophiolite sequences studied in Waziristan, West Pakistan, this is the Suleiman Ranges, and also in Mazira off the east coast of Arabia and in Oman. All of this shows a similar sort of timing to when Tethys withdrew. Okay, so here's a rough tectonic sketch showing how a reconstruction is showing the Spontang ophiolite and the Spong Arc. This is going back to about 80 million years. And then the ophiolite was abducted onto the continental margin of India. And at this time, there was another oceanic subduction zone to the north in the Dras-Kohistan Arc and underneath the Ladakh batholith. Two continents collide, suture zones either side of the Kohistan-Dras Arc collide. And after this, this is the timing of major crustal thickening. So here's another diagram showing the same thing. These are all the age data that we have from the granites, the Ladakh granites, and this is the stratigraphy data and the biostrat data, which tells us that the marine continental transition occurred at 50 million years. Okay, so what happened on the Zanskar Shelf? This picture here is taken looking over the Zanskar Shelf from the top of, I can't remember the name of the pass, but it's the one above Zangla, going from Zangla towards Marka, Zhunglam route. Absolutely spectacular place. All of this is in unmetamorphosed Mesozoic shelf carbonates of the Zanskar range. In yellow is just tracing around bedding, around the folds. And in red are thrust faults or detachments. So after the collision, there was an enormous amount of crustal shortening and thickening as a result of this folding and thrusting. Here's another spectacular example. This is just above the village of Photoksa in the Mesozoic unmetamorphosed shelf. And the yellow is just tracing around bedding, and the red are detachment faults. And one more, which I can't resist because it has an absolutely incredible structure here, which is a refolded fold, classic refolded fold. So the amounts of shortening and crustal thickening were very, very large, at least 100 kilometers plus, just across that section of the Tethyan zone. This is a picture from the winter trek we did down the Zanskar River. Now this area is you cannot get into in the summer at all. There's no villages there, there's no trails. The river is enormous, it's very rough. People canoe down it, kayak down it. But we went in January and the river was frozen. So again, you've got spectacular examples of folds and thrusts in the main shelf carbonate sequence here. Okay, just to finish, a few nice pictures of the fieldwork. This is flying into Leh. You get the beautiful view of Nun Kun and the Suru Valley. This is the Zanskar Valley here. Padam is about there. This is the mountain of Kun, east face of Kun, and all the metamorphic rocks around the Suru Valley. This is the main trekking route south of the Indus. The old rope bridges, which unfortunately have largely disappeared in Zanskar now. And where you don't get bridges, you're reliant on horses. And these are my two very good friends, Fida Hussain, who's now passed away, unfortunately, from Leh, and Sonam Targis from Marka, who's also passed away. And this is an old picture of Leh in the 1980s when I first went there. Absolutely wonderful, magical place. Here's Sonam Targis, very, very spectacularly good guide, knows every valley in the Zanskar region. And this is one of the bridges that we crossed in the eastern part of Zanskar in the old days. I think if those haven't fallen down, they've largely been replaced. This is the old Zanskar bridge at Zangla, which is one of the most famous rope bridges. And the monasteries at Sani Gompa and Spituk, just near Leh. A few pictures from our frozen trip, our trip down the frozen river. Very, very dangerous. The ice is only a few inches thick here. And there were 4 of us from Pishu and 3 of us. And when camping on the sides of the river, it took us, I think, 7 days to walk from Chiling down to Padam. And then when we got to Karsha, you could put skis on and ski across the plains of Pipiting. But the river was like this. It was incredibly cold, very dangerous, spectacular geology, and a wonderful place. Okay, 2 slides to finish off with. This one here is a reconstruction of the India-Asia collision. This is the Asian plate, the Ladakh granites. This is the Indian plate, spontaneous ophiolite abducted onto the Mesozoic passive continental margin of India, which was part of the great Indian Archean shield overlain by the Proterozoic and the Mesozoic thick shelf carbonates of the Mesozoic, same shelf carbonates you see all along Oman, Arabia, Zagros, etc. And then after the collision, or immediately during the timing of collision, the leading margin of India, Somarari, TM, was subducted down to eclogite depths down here, and then extruded back up the way it came. So then during the crustal thickening phase of the greater Himalayan sequence, Somarari is now entrained in the lower crust of the Indian plate, right next to the Indus Molasse basin above it. And then all of this shows thickening to kyanite grade metamorphism. So 30, 40, 50 kilometer thickness, 50 kilometer thickness of Indian shelf carbonates and Proterozoic underneath it. And then the decompression from kyanite grade to sillimanite grade, this is the timing of formation of all the Himalayan leucogranites, like for example at Gumbarangjum in Zanskar. So you're going from the early kyanite grade, which is 40, 35 million years, to the timing of sillimanite grade metamorphism, migmatites and leucogranites, which is all around 20 million years. And that is the end of my story. So Himalayas, very beautiful, simple mountain range. Indian plate prior to the collision, composed of the Archean shield overlain by thick Proterozoic. We never see Archean rocks in the Himalaya, but we know that they must be under thrusting to the north simply by balancing cross sections across the upper crust. You know that the Archean lower crust must have under thrusted the Ladakh, the Lhasa block, probably by 200 or 300 kilometers. And then all the intense folding occurs mostly in the Mesozoic and the Paleozoic, and the channel flow affected dominantly the High Manta formation, which is the protolith of all the sillimanite gneisses and leucogranites. Okay, well, thank you very much for listening. I'll be happy to answer any questions you have. So over to you, Ritesh.
Thank you, Mike. Surely it was a very, very, must say, enlightening talk from your part. All the structural features which we used to see, right from Zanskar, the first slide which you showed, just near Zangla, to the Ladakh and Changthang areas, especially the Chumathang leucogranites and the granites. And the way you explained, everything was quite interesting. And I must say, the detailed work you have done has really made the Himalayas look very simple. Your experience in working in India, you're working in Tibet, in Southeast Asia, and also in Oman, has helped to build a very clear picture of the entire Himalayan formation, which you have showed in your presentation. Now, I have just a few queries, or before that, I can just ask Professor Talat, if anybody anybody else wants to ask. Yeah.
Thank you, Ritish. Yeah, Mike, it was beautiful, very nice presentation, very, very clear, and definitely any confusion that people had must be clear. But still, if there is any question, we will be very happy that Mike will reply to those.
Sure.
Please identify yourself also when you're asking any question, yeah?
We have with us Owen Green also.
Yeah.
Owen Green, welcome to the webinar.
So good. I wonder if somebody has any question.
So, Talat sir, I like to ask one or two questions maybe.
Please.
So, Mike, as we were discussing earlier also, your presentation limits the marine sequence in Himalayas to about 50 million years, yes, approximately.
Correct.
And now that is quite obvious because all the specimens which we are getting in the Sabatu Formation and also in the equivalent homotaxial equivalents in Myanmar and Leh Ladakh and also in Kargil sequence, we are getting almost the same sequence of the same type.
Mm-hmm.
So that is just one aspect of it now, because they may be, you can say they are just dated at the time of their formation. The dates which they are showing are the dates which they were formed or at the time which they were deposited. So, but if we do the paleo environmental reconstruction now, or the paleo latitudinal position at the time of deposition of those sediments, then it will be very interesting, because as I was earlier discussing, like maybe these Eocene sequences, the pneumolites or other fossils which we are getting, they were not deposited at the time of deposition. The paleolatitudinal position may be quite different. And to support that, I just want to share some observations which we have done or some discoveries which we made while doing, as I was discussing with you, some plant fossils. So the pneumolites may move and the seas, but the plants have some very fixed positions. So we found in 89, 90, we found a lot of plant fossils from Kasoli, and on 6 or 7 species we were able to identify. The Kasoli sediments represent continental environment, as you said also, like Hemis or Nerula formation which you showed. They all represent continental environment. But interesting thing was, these were very continental conditions, but they were near coastal environments. They were not actually continental, but they were near coastal environments. That is what our study showed. And then these papers are published and also part of my thesis. Then those 6 species are nowhere found in Himalayas now, and then they are confined to the Indo-Malayan region, India, Indonesia and Malaysia, and maybe Andaman Nicobar today's modern counterparts. So on the basis of that, the Sabatu formations which we're getting in the Ladakh Himalayas, which you showed, or maybe other parts of Himalayas which we're getting, and the palm fossils also, which were reported earlier by various institutes and also reported by us, and hippopotamus fossils also reported from Ladakh. So all these, our species from Kasoli, they show very strong affinities that at the time of deposition, the paleo-latitudinal position was near the equator. So that makes the entire story quite interesting now. So if the Kasoli formation is dated around 20 million years, and equivalent formations in Himalayas, in Narula, also almost, if you say, then the nummulitic limestone which you showed and the sandstone in Narula which you showed was quite interesting because we found a lot of fossils of logwoods in Narula sandstone, though not very well preserved, but yes, logs of wood were found in Narula. So that was interesting, but there was something missing, I think, there, or you can say similar equivalent. So the paleogeographic conditions of depositions, the paleolatitudinal depositions of these Himalayan fossils which we are getting, has to be taken into consideration while reconstructing the actual position of the fossils which we are getting in the Himalayas now. So that our study shows that at maybe all, if Kasolis are approximately 20 million years and they are near the equator, then all the other this Eocene sequence has to be near the equator or south of that, you know, maybe 4 to 11 degrees north of equator. And then if it is that 20 million years, then the Himalayas were not born at that time. And things have to be taken in that perspective, because those plants need to be explained while we are while we are trying to understand the timing of collision. So
there's a lot of
marine influence ends there, as you said, in 50 million years, but near coastal environmental influence maybe continue to persist for long, you know. So
can I answer?
Yes.
Okay, one thing is that the marine fossils, the nummulites, acylinas, and everything, were definitively forming at the timing that I mentioned, that Owen's been working on. And they definitively state that there was marine sedimentation there. Everything along the Indus suture zone after 50 million years is continental. They're red beds. They were not deposited anywhere in an ocean. They're rusty. They're full of lake sediments, river sediments, the hemiscontinental molasse. Now, where people get confused is that there are younger marine sediments, for example, in the Sulayman ranges around the west side of Pakistan. Those have nothing to do with the India-Asia collision. If you imagine the Arabian plate colliding with Iran, that collision occurred 20 to 22 million years ago, but there is still marine sedimentation in the Persian Gulf, the Arabian Gulf today. That is happening in the Fallen Basin of the Zagros. So you can easily have marine sedimentation to the south of India or to the west in Pakistan, but that is not dating India-Asia collision. Dating India-Asia collision must be done along the Indus suture zone and on the immediate northern boundary of the Himalayas in Zanskar, Ladakh. And that's what all of our work and Owen's dating has told us. So I think the marine to continental transition in Ladakh is absolutely firm. You can't argue with it. The paleomag tells you that, the biostratigraphy tells you that, the structural geology tells you that. What is happening to the south of India in the Siwaliks is nothing whatever to do with the collision of India and Asia. That could easily have marine sedimentation in the Lesser Himalayas going on younger, but it's not telling you about the India-Asia collision.
Okay, thank you, Mike. Is there any other question? Maybe a short one.
Yeah, I like just to make some point, because you know that you can say at Numa or maybe in Leh also in the granites and south of that.
Dr. Arya, there is a question in the chat as well. Kindly.
Okay. Please, sir. You can just ask them.
Yeah. This is a question by Mahesh Thakkar, and he says that, dear Mike, the lecture was absolutely clear and highly informative. I have a question, whether the nummulites found along the molasses at Suture are deposited in the similar condition when the passive margin sediments at Kutch, Pakistan, Iran, and Oman. I repeat, I have a question whether the nummulites found along the molasses at Sucher are deposited in the similar condition whence the passive margin sediments at Kutch, Pakistan, Iran, and Oman.
I suggest that Owen is the best person to answer this.
So Owen, we request you to please come and answer this.
Yeah, I think from what we've found, when we're looking, and we have done some work in Oman, that yes, the nummulite assemblages are very similar to one another, and I would suggest that yes, there is sort of, this was all occurring at the same time, or at least not many million years difference between them. At least that's what we're finding when we're looking at our assemblages. Because there is this issue with nummulites in that they do not, they don't show the same sort of evolutionary advances that you might get in, say, planktonic foraminiferous, not the same pace. So the zones that we're using, the shallow benthic zonation schemes that we're applying to this, involve looking at a range of different genera that might occur in that, in the sedimentary rocks that you've got there, in the final marine rocks. So I can't comment too much on Pakistan, but I think, Mike has been there. We've certainly looked at, or I've certainly seen rocks from Pakistan which appear to contain nummulites and acylinids of a very similar age. And again, the same with Iran. I'm not really sure if they're exactly the same assemblages there.
Sir, your mic is on, please. Okay. Yeah, please, Owen, please continue.
Yeah, Ritesh, I thought you made an interesting comment about the paleolatitude and what your plant material is indicating there. And I must admit, that's something which I don't think we looked at in too much detail, what paleolatitude this was all occurring at, whether or not we were just south of the equator or just north of it. That was quite an interesting point. I wouldn't mind reading up more on that if you've got a paper on it. Yeah, that would be good to see. Yeah,
and I just like to add one more thing, that in while we were doing some projects for the Indian Army in Newma, we found very good oyster bands and bivalves and gastropods, which were quite similar to the ones which we find in the Sabatu Formation, in Himachal Pradesh.
Yeah.
And this is not reported by me only, but Wadia Institute, Mathur sir and Jual sir, they also reported something like this in a very, very preliminary findings in their paper published long back, But that was from Leh. So, but we could extend this boundary from Leh to Newma. So Newma also, that sea was like extending. So this is quite interesting, and I would be interested, Owen, if you can just comment or maybe give a thought about the paleolatitudinal depositional environment of these nummulites, because that could be quite interesting. Because whether this sea was deposited, because we are finding a lot of megafossils not only plants, but also mega faunal evidences, which suggest that we cannot get hippopotamus in Ladakh. It is impossible, to get that. And the palms, it is impossible to get the palms in Ladakh at 30 degrees north, or 32 degrees north. But they have to be somewhere near the equator to get all these floral evidences, because otherwise then we found very interesting find was we have a granite and we have a sandstone of Indus Moles, you call it, but I call it equivalent to Kasolis, that is about 20 million years rocks. They are almost at one contact. We are finding fossilized wood in the sandstone and the granite contact. That is not practically possible in an environment when we are talking about the volcanic activity and also the sedimentation. So sedimentation and this Hemis formation has to be thought about in a different, very, very different angle, because Hemis conglomerates are not all of them, not, I'll say 90% of them are not from the granite, you know. They are not derived from the granite. You can easily say, you know, and also the drilling samples which we done along the Indus-Sucha zone say volumes about not granite samples. None of the granite samples we get after about 20 feet or 30 feet, you know. It's all about the different volcanic pebbles or horizons which you get from different, maybe transported from Mansarovar and things like that, you know. So
Ritesh, I don't think that's too true, Ritesh, because there's been a number of papers out on very detailed papers on the Hemis conglomerates, and 90% of the boulders in the Hemis conglomerates are derived from the Ladakh granite. There's a few andesites in there. There is almost nothing derived from the shelf carbonates to the south.
No, I'm not talking about south. You know, it has to be from the north only, or maybe this entire thing has to be thought about in a different angle. You know, because we don't find granites in all the specimens. You know, in Lato also.
Ritesh, we have also seen there are 80 to 90% clasts are from granite towards the north. And then towards south, when you go, you have some of the more mafic material or class, which may have come from the ophiolites. So I doubt that you will bring this from such.
Sir, but if you see that conglomerate horizons, then we have this sandstone also, and then from those sandstone intercalated between conglomeratic horizons and the sandstones. In the sandstones, we get beautiful preserved palm leaves, beautiful logs, and then explaining all these palm leaves in the paleolatitudinal conditions which we are seeing today is a very, very dicey proposition as far as interpreting these fossils. And yes, you can say that, yes, you get everything from there, but the fossil evidence doesn't suggest, doesn't support whatever has been suggested, you know, because it is not a distance of, I'm not talking about kilometers, I'm just talking about less than 100 feet difference. We get a Ladakh batholith and we get a fossilized wood samples, and all the fossilized wood or maybe oysters which we are getting, they have nothing to do with this Ladakh batholith. Or maybe another interesting thing, Talat sir, you are also here, maybe you will be able to answer this very good, you know, and Michael. So what led to the evolution and upliftment of the Ladakh batholith? You know, that is quite interesting for me. You know, if you can answer that, maybe that is slightly not out of your talk, but this could be very interesting for me to know when and how the Ladakh batholiths were evolved, and how were they able to attain these great heights? You know. That would be quite interesting if anybody can answer
that. We have dated some of the class, okay, which is about 16 million years, 16 million years. So definitely granite will be at depth, and then it has to exhume, but come out.
So, but what were the forces? Yeah, I will be more interested to know what were the forces responsible for making these great heights of these batholiths, you know, about 18,000 feet here, which we see. That would be quite interesting, you know. So any explanation for these, how these batholiths or the granites, which were formed at great depths, attained these great heights of about maybe 6,000 meters only in Ladakh, or maybe in other parts they may have attained that great height.
Ritesh, it's very common along the Andes that you have the situation in Ladakh, along the Ladakh Gangdesi granites was very similar to what you see in the Andes today, where you have thick crust, high mountains, dominated by Andean type granodiorites, granites, and andesite, dacite, rhyolite volcanics. And those volcanics are erupted onto young lake sediments, onto red bed deposits. So it's absolutely no problem at all to have fossiliferous red beds right next to a Ladakh type granite. If you imagine the Andes today, that is exactly what the Ladakh Asian margin Gangdesi looked like prior to the collision. And then the underthrust, it's quite possible that the Gangdesi Ladakh granites, the southern margin of Asia, was high and thick prior to the collision, similar to the Andes today. But there is no question that there is increased elevation in the Ladakh granites since the collision, and that is because of the underthrusting of India. It's like putting a jack underneath a car and you jack it up.
Yeah, definitely the granite will form at some depth. It has to. Now we know that it is there. And you see the class. So timing-wise, some of the class are about 16 million years, even younger. Okay, that means it has been going on. And in the southern part, you have possibility of also getting the class from the these ophiolites. Okay, that's what I would say. And Mike, I just wanted to check with you. You have also dated, and we have also done near this Karakoram fault. You have these 20, 21, 18 million years. Do we have similar thing near Chumathang? Because almost same sort of dikes. Did you get some younger age? Yeah.
Yes, there's young leucogranites all the way along the Karakoram fault, and we've done many, many years of dating work along them. So we know the timing of the leucogranites in the Karakoram very well. And the strange thing is in Ladakh is that you would not really expect leucogranites in an Andean type continent, but there are two areas where they're very abundant. One is Chumatang, and the other is in the Indus confluence in Pakistan. Both of those are the very, very final magmatic phase coming out of an Andean type granite. So they are garnet and biotite bearing leucogranite, but they are really fractionates of the old biotite hornblende granodiorite. So they are nothing like the Himalayas. The strontium initial ratios are much less than the high Himalayan granites.
Okay, very nice. If there is no more question, I don't know
Sir,
whether we have more time or we close it.
I just ask Professor Kishan Kant to just give a brief about the museum and thank everybody.
Yeah, that will be nice.
Professor Kishan, are you here?
Yeah, thank you very much, Dr. Arya, for this wonderful lecture that you have arranged today. And Mr. Mike Searle and Owen Green, really thankful to you for giving this insightful talk. So it is, of course, the responsibility of our organization to organize such functions time to time. And this webinar as such, if I would say, it was organized by members of Tethys Fossil Museum and Research Center. And we have been organizing such sessions every month. And you all are welcome for that. The museum as such is coming up at Dangiari, a small village in Kasauli Tehsil of Indian Himalayas. Geologically, museum is located on the debris concealing the Dakshai-Sabatu boundary, which signifies closure of Tethys Sea and evolution of terrestrial ecosystem. The museum is built from 20 million year-old rocks of Kasauli sandstone, beautifully chiseled to give museum an aesthetic look. Water which we drink in the museum is from a borewell drilled into 40 million years old white quartzite sandstone, which is a marker bed extending from Pakistan to Burma in the east. Tethys Museum will display diverse, well-preserved fossils of stromatolites, Ediacara, trilobites, mollusks, ammonites, etc. from Spiti Valley. Fishes, whales, other things. All these things are there that we always come across when we visit this beautiful museum, which is there. And oysters, molluscan foraminifera from Subatu and Leh, plant remains consisting of logs of trees, leaves, flowers, roots, as was discussed by Dr. Arya during his discussions today. These all are from Kasauli and Dharamshala, and mammals from Shiwaliks, signifying gradual evolution of life on this planet, and all are part of the museum repository. So anyone visiting the museum will have a glimpse of these beautiful things that have been collected with a long effort and strenuous effort, of course. The museum will have a glimpse of how different fossils collected from different geological formations across the Himalayas can help to rebuild the entire paleohistory of various events which led to the evolution and birth of the Himalayas. Tethys, as we all know, was an ocean once upon a time separating India from Tibet and Eurasia, as has been very well discussed today by our guests. As the Indian plate moved northward and Tethys squeezed, and when the two plates collided, the Tethian sediments were uplifted, forming the mighty Himalayas. And lots of research has been done in timing the collisions of the two plates, leading to evolution and birth of the Tethian Himalaya. But still there is no consensus, and there are Himalayan opportunities for researchers to come up with a convincing module to time the collision and explain the birth of the Himalayas. Keeping this in mind, the organizing committee of Tethys Fossil Museum and Research Center, they decided to host a series of lectures on the given topic by veteran geologists who decided and dedicated their lives to understand this geomechanism which is coming up. Thanks a lot once again, the researchers of today, that is Mr. Mike Searle and Owen Green from the University of Oxford. I'm thankful to you on behalf of Tethys Fossil Museum in India. And do visit our museum whenever you are around India, and we would love your visit to the museum very soon. All others who were there in the meeting today, especially Dr. Ritesh Arya, who is the host, and Mr. Talat Ahmed, Bashir Ahmed, Dr. Sudesh Vidhavan, Ridyan Chauhan, Ihsan, Irfan Bhatt, Mahesh Thakkar, and others who participated in this today's discussion and made it a lively show. I'm thankful to you all for being here today. And thanks a lot, Dr. Arya, once again. Thanks a lot to all my dear friends. Thank you very much.
Thank you.
Thank you very much indeed.
Just before ending, can I request, Owen, can you be our next guest? Every 22nd of every month we organize this meet. So any 22nd of any month, if you're free, as Michael said, that we'll be very much interested to know the fossil evidences from the entire Himalayas which we have collected. Yeah. So if you're free next month, we can arrange a talk on 22nd. Is it okay with you?
Yeah, send me an email and I'll check with everything when I'm at work and see what I'm doing, and we'll arrange.
So that would be quite interesting, and we'll be happy to host you as our next speaker. You know?
Thank you.
Thank you. Thank you, Mike. It was quite pleasing to have you and listen to you. We have been reading your papers and your books, but to see you and have interaction with you was really great. And thank you, Professor Talat, for sparing your valuable time.
Okay.
Thank you very much.
Welcome.
Thank you very much.
Bye-bye.
Bye-bye, Talat. Thank you very much, Ritesh. Very pleasant. Bye-bye.
Bye. Cheers, Mike.
See you, Anne.
Dr. Arya, kindly end the meeting. Dr. Arya.